everybody. This is Olenjolai from United Republic of Tanzania. That's a beautiful country where I'm living. I would like to just welcome you into this fantastic YouTube channel that's called Tanzania Online A-Level Secondary Schools. In square bracket is Olenjolai. There is no these kinds of the dotted lines. This is during the teaching process. Okay, so this program or this program, it is for the serious A-level students who want to master the concepts of advanced chemistry. That the department where we are, and the subject that I'm going to teach you in this video is called advanced chemistry. And the main topic is general chemistry, and the topic of the day is atomic structure. And then the concept that I'm going to teach you is called quantum number. This is lecture or session or video 12. So if this is your first video that you are watching by, then you have to make sure that you watch the previous 11 videos before you come to this. And then this is a continuation of lecture or sessions or video 11 that we have introduced the quantum number, and I taught you only one quantum number and I left the homework there. So in case you have questions, because I like my classes to be so interactive, so I would like to ask you that to use the digital platform to ask your questions, which is the comment sections of this video. You can ask your questions and then I will try my level best to answer. Remember that I don't know everything concerning about the general chemistry or advanced chemistry, I just know small portions of it. But I'm ready to pass that knowledge to you so it can assist you in your A-level studies, or in your diploma studies, or in your undergraduate studies, or in your daily life, maybe in your laboratories, maybe you are working somewhere else that you are using chemistry in everyday life, maybe in your small industry, maybe you're in a small enterprise that actually that you are using the concepts of the chemistry. So let us go together on learning about the quantum number as a subtopic of 40 of the atomic structure. So in previous lecture, I would like to see that display. Okay, in previous lecture, I told you about, first of all, we defined what the meanings of the quantum number. So the definitions of the quantum number. Do you remember that the definitions, how we define about the quantum number? I told you the quantum number as a set, the quantum numbers are the set of the numbers used to describe the positions and energy of electrons in an atom. So basically, I taught you about definition of quantum number, right? Quantum number, taught you about that. Then I taught you about types of quantum number. This is a very important part of hydrogen spectrums. Types of what? Of quantum number. And then we found that there are 4 types of the quantum number. The first one we call the principal quantum number, its notation is N. The second one we call the subsidiary quantum number, its notation symbol is L. The third one is called magnetic quantum number, its symbol is M. And then the last one we call magnetic, or we call it spine quantum number. So we have 4 quantum number: principal quantum number, subsidiary quantum number, or angular quantum number, magnetic quantum number, spin quantum number. In lecture 11, we covered about this, and then we told you, or I told you about applications, or what are the applications of what? Applications of principal quantum number. First of all, we define what the means of principal quantum number, and then we learn that the principal quantum number can be represented by the positive integers 1, 2, 3, 4, etc. But also it can be used, or it can be, we can use the capital letters that K, L, K stands for 1, L stands for 2, and then M stands for K, L, M stands for 3, then N stands for 4. So these are the notations for the principal quantum number. Then I told you 3 applications of the principal quantum number. Then I left a homework for you that to describe briefly what the means of subsidiary quantum number. Did you do it before I do the corrections or I teach about that? Have you done it? Ask yourself, why didn't you do? You're waiting for me just to teach you without bothering yourself? No, that is not a good student, because a good student has also to participate. You know that actually that in educational systems, in United Republic of Tanzania educational system, and even in the world educational system, even if you check the US educational system, so the United Kingdom's educational system, the teacher has to provide 25% of the content. So 75% has to be found by the student. Possibly I'm doing vice versa, that I'm giving you 75%, but you fail even contribute your 25%. Please, 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 please be a good student who doing and trying to do the homeworks. I'll be leaving in every lecture. Okay, so let us continue. So today, I'm going to teach you the second quantum number. We call it the subsidiary. So if you did, congratulations. If you did the homework, congratulations. If you didn't do, I'm very sorry, because I don't like lazy students. I'm not lazy, and I don't like lazy students. Subsidiary quantum number. So I'm going to teach you about subsidiary quantum number. So say subsidiary quantum number. Quantum number. Subsidiary quantum number. And this will have notations of L, lowercase l. Subsidiary quantum number. Okay. Before we define what the means of subsidiary quantum number, we say that subsidiary quantum number, okay, subsidiary quantum number is also called, in chemistry code, is also called Azimuth, called Azimuth quantum number, Azimuth quantum number, and hence also can call it angular momentum quantum number, angular momentum quantum number, so angular momentum quantum number, and also this subsidiary, or as Musso, we call it orbital quantum number. So another name we call it orbital quantum number. Orbital quantum number. So we can call it subsidiary, or we can call it azimuth, we can call it angular momentum, we can call it orbital quantum number. So all of those four names are very important. So now allow me to go to the basic question, that what is azimuth, or what is subsidiary, or what is angular momentum quantum number, or what is orbital quantum number, right? Quantum number. So what does it mean, right? So I found one definition for you. So you say subsidiary quantum number, we say that is the energy, is a sub-energy level, is sub-energy level in which electrons or electron is placed and it specifies the shape of orbital of an electron. And specify the shape of orbital of electron. So you say azimuth or subsidiary quantum number, we say that is a sub-energy level. So it means that the sub-energy level, if you compare the principal quantum number, in which electron is placed, and also in this subsidiary quantum number specify the shape of the orbital of electrons. So we'll be learning about shape of the different orbitals. We'll be learning first the fundamental orbitals. We'll be learning a lot of things in that Musso. As Musso quantum number, I cannot say that it's the most important compared to the other 3, no, but it's giving us many information compared to other 3 quantum numbers. So that's the definitions of Asmuso quantum number. Again, we say that we like to see for the notation, and then we like to see that how we can have notations of it and enjoy the beauty of chemistry. In chemistry, in quantum, let's say quantum, or in atomic structure, let's say, because we can study chemistry or physics, in atomic structure, the subsidiary quantum number or sub-energy level, subsidiary quantum number is notated or denoted as what? As L. So that's the notation. So subsidiary quantum number, instead of saying subsidiary quantum number, in case we write L, it means that subsidiary quantum number. So the relationship or before we say that before even I teach about the relationship with the principal quantum number, we say that the subsidiary quantum number takes the values of 0 and the positive integers. Very important sentence. So we expect to find that the subsidiary quantum number of an electrons to be either to have a value of 0 or positive integers. Right? Positive integers. This is very interesting. So you say again, the relationship, we have to learn, let me teach you the relationship between principal quantum number n and the subsidiary quantum number L. So we say that L, subsidiary quantum number, is equal to 0 up to n minus 1. This is a very important formula. So you say the general formula of subsidiary quantum number of L is this. L is equal to 0 dash 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 to n minus 1. Very important formula. And I'll teach you soon what does that formula mean. What does formula mean? So again, that the relationship, because n represents the principal quantum number. So now, from this formula, we have the relationship between subsidiary quantum number L and the principal quantum number n minus 1. Okay. So now I would like just to clarify more about this relationship. We say that suppose here we have principal quantum number. Listen careful. Suppose that on this side we have principal quantum number, principal quantum number, and then on this side suppose that we have subsidiary or Asmuso quantum number. So we want to see the relationship. So here the notation is n. On this side, L is equal to 0 dash 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 to n minus 1. Listen careful. Suppose that the principal quantum number is equal to 1, because this is the ground state. We call it ground state of an atom. or ground state, or we call it the stationary state. N is equal to 1. So what will be the principal, the subsidiary quantum number? Subsidiary quantum number for this case will be 0. Why 0? Because it will be 0, then the next number will be 1 minus 1, which is equal to 0. Okay, so this is the first example. The second example, what if we got the second energy level, which is n is equal to 2? Hence, what will be the value of subsidiary quantum number? So remember that you can have even lines like this for you to understand them clearly. So L, we say that this is 0. First, we start from 0. And then if there's any number, is fine. But if there is no, then we have 2 minus 1. N is equal to 2. So remember that here we have 0. The next one is 1 minus 1, which is still 0. So it means for this case, subsidiary quantum number. Listen and look careful. What I'm teaching you is very important, and you can struggle to understand it. So 0, so this is 0. The principal of the subsidiary quantum number is equal to 0. 2 minus 1 is equal to 1. So here we have two subsidiary quantum number. The first one, L is equal to 0. The second one is equal to L is equal to 1. Again, we continue. I'm teaching relationship between subsidiary quantum number and the principal quantum number, which I taught you in lecture 11, which I believe that we covered it before this. Again, can go for number 3. Okay, can go for number 3. When n is equal to 3, principal quantum number is equal to 3. L is equal to what? First is equal to 0. Then the second one will be what? N minus 2. And then we go for n minus 1. Right? So what does it mean? Because this is n minus 3. So before, it means the general formula, the first value of L, because we have n is equal to 3, L is equal to n minus 3. Then the next one will be n minus 2. The next one will be n minus 1. Means that it's what in descending order. So if that the case for the value of n is equal to 3 minus 3, then n is equal to 3 minus 2, then n is equal to 3 minus 1. So L is equal to what? 0. 3 minus 2, it is 1. 3 minus 1, it is what? 2. So here we have 3 subsidiary quantum number. The first one, subsidiary quantum number is equal to 0. Second one, subsidiary quantum number is equal to 1. Third one, subsidiary quantum number is equal to 2. Right? I'm teaching you slowly because I know that this is new concept for you. 10. Then we go. If you have n is equal to 4, the fourth energy level. So we say that the general formula for subsidiary quantum number will be n minus 4, comma, n minus 3, comma, n minus 2, comma, n minus 1. So subsidiary quantum number is equal to 4 minus 4, then 4 minus 3, then 4 minus 2, then 4 minus 1. So then now the subsidiary quantum number 4 minus 4 it is 0, 4 minus 3 it is 1. This is the simplest way of learning. 4 minus 2 it is 2, 4 minus 3 it is what? It is 3. So here we have how many subsidiary quantum number? 4. The first subsidiary quantum number is equal to 0. Secondly, L is equal to 1. Third, L is equal to 2. Fourth, L is equal to what? 3. So then now, let me leave you the homework for you when n is equal to 5. So what will be the value of L? Give me the general formula and also give me the subsidiary quantum numbers. Okay, so now you know the relationship between the principal quantum number and subsidiary quantum number. Remember that the interest or the point of interest is not, because we have discussed that where the electrons used to be placed is in principal quantum number, but the main functions of subsidiary quantum number is to mean that to show or to give us information about the orbit, the shape of the orbitals. Okay? So we say that another piece of information we might get, each number refers to the specific type of the orbital. Okay? So we say that the shape, so like just that we say that the relationship between the, yes, for a teacher of the shape, we say that the relationship, we don't know the shape yet, relationship between principal or subsidiary quantum number L and the shapes of the orbital. Shapes of the orbital. Shapes of the orbital. Like just to introduce you the shapes of the orbital. I haven't taught you yet. I'll teach you soon, but I'd like to introduce to you. We say that when subsidiary quantum number L is equal to 0, this means that, or it represents that L is equal to 0 stands for S orbital. Say S orbital. S orbital. There's a long terms for these terms. S orbital, because S is spherical, we say that, yes, S is sharp. So it's a sharp orbit. See, so S stands for the word sharp. So sharp orbital. So we say when again, because we found the subsidiary quantum number is equal to 0 from n is equal to 1. So it means in the first energy level we have what? The S orbital. Again, so when it comes to the second energy level, we found that also the one value of L is 0. What does it mean? This is S orbital. So even in the second energy level, n is equal to 2, we have what? S orbital or sharp orbital. Again, so when n is equal to 3, we found one value L is equal to 0. What does it mean? So we say that the shape of L, or the shape, means that the principal quantum number n is equal to 3 also contains the S orbital. Again, when n is equal to 4, we found that one value of subsidiary quantum number is 0. What does it mean? It means that the principal quantum number n is equal to 4 contains one S orbital. So then again, we say this is 1. Let us go to, we say when the value of subsidiary quantum number is equal to 1, what does this present? So this stands for diffuse. Say diffuse. Diffuse orbital. Diffuse, or we call it D orbital. D orbital. So this we call it D orbital. When L is equal to 1, stands for diffuse or D orbital. Okay. So that is when L is equal to 1. So what does it mean? The principle, the first energy level whereby n is equal to 1 does not have the D orbital. The second energy level, it has L is equal to 1, it has one D orbital. The third energy level, n is equal to 3, one L is equal to 1, it has a D orbital. That's the beauty of quantum number, it's beautiful. And then when the principal quantum number is equal to 4, n is equal to 4, then one of the subsidiary quantum number is equal to 1. So we have D orbital in the fourth principal quantum number. So this we call diffuse, the long terms. But in chemistry, just we call it S orbital and the D orbital. Then Roman 4 or Roman 3, we say that when the value of subsidiary quantum number is equal to 2, what does this stand? This stands a specific shape. And this shape, we call it F. And call it O. Excuse me. This is not diffuse orbital. This is P. So the long terms of P orbital, we call it principal. This is principal. Excuse me for this mistake, principal. So we call it P orbital. So in short, in chemistry, we call this as what? P orbital. So when L is equal to 2, that stands for what? stands for diffuse now. What I mentioned Roman 2. Diffuse, in short we call it D orbital. So it is D orbital. So we say that the orbital there it is what? It is D orbital. Then we go for Roman 4. When the principal quantum number n is equal to what? L is equal to 3. What does this state? What does this stand for? This stands for another new orbital, which we call the fundamental. Fundamental orbital. In short, we call it F orbital. So in short, we call it F orbital. So listen carefully. When n is equal to 3, one value subsidiary quantum number is equal to 2. What does it mean? It means when subsidiary quantum number is equal to 2, the shape of the orbital here is diffused, means it is d orbital. Also, when n is equal to 4, one of the subsidiary quantum number is equal to 2. So what does it mean? It means the shape of this orbital is d orbital. When n is equal to 5, I gave you the homework. Again, when n is equal to 3, it ends to n is equal to L is equal to 2. When n is equal to 4, one of the value subsidiary quantum number is 3. So this indicating that this is what fundamental or F orbital. So it means that the principal quantum number or the principal energy, the principal quantum number n is equal to 3, n is equal to 2, n is equal to 1, don't have the fundamental orbital. So we find the fundamental orbital when n start to get into 4. So when n is equal to 4, we have all the 4 orbitals. The S orbital, the P orbital, the D orbital, the F orbital. Interesting. So if that's the case now, we find that according to the table that had, we may generalize that this piece of information, which is very important. If that's the case, the principal quantum number n is equal to 1 has how many orbitals? Only 1. So the principal quantum number n is equal to 1 has only SC orbital. And the principal number n is equal to 2 has S orbital and the P orbital. Because you have L is equal to 0 and L is equal to 1. The principal quantum number n is equal to 3 has 3 orbitals. Has the S orbital, the P orbital, and the D orbital. So the principal quantum number n is equal to 3 has 4 orbitals. Has S orbital, then P orbital, D orbital, and the F orbital. Okay, so that's the summary. So I have introduced to you the concepts called the orbital as the key point of subsidiary quantum number. Now I would like to teach you about the shapes of the orbital. I'm trying to summarize according to the requirements of your syllabus. This is intensive subject of atomic structure. Shapes of orbitals. Say shapes of orbitals. Shapes of the atomic orbitals. Shapes of the atomic orbitals. Shapes of atomic orbitals. So I have to teach you about the shapes of atomic orbitals. We say that in atomic structure there are 4 types of orbitals, which are, number 1, we say that sharp, which we call it in short S orbital. Number 2, principal or P orbital. Principal orbital. Then number 3, we have what? We have also diffuse or the orbital. Number 4, we have fundamental, or in short we call it F orbital. So in summary, the 4 orbitals are known as 1, S orbital, 2, P orbital, 3, F orbital, D orbital, and then 4, F orbital. Question. It's the beauty of chemistry. So this part, I've just introduced to you the orbitals that we have in chemistry. Okay, the orbitals that we have in chemistry. But now let me teach you the shapes. Okay, the shapes of these orbitals. So we have to start with number 1, the shape of S orbital. Say with me. Bear this in your mind. Even if you forget what I taught you today, make sure that you remember these 4 orbitals. Okay? The shape of this S orbital. So we say that the shape of S orbital is spherical. The radius of the sphere of S orbital increases, this increase in what? This increase with increase in the value of principal quantum number. Principal quantum number. So we say that this is spherical. So we can draw the sphere. This is the shape of 40 of S orbital. So we say that the shape of 40 shape of S orbital. What does this sentence mean? It means when the principal quantity, or when the principal example, the radius of, because here in n is equal to 1, we have one S orbital. Listen carefully. When n is equal to 1, we have one S orbital. When n is equal to 4, we have one S orbital. But the radius of this S orbital, when n is equal to 1, is smaller than radius of this S orbital. Because remember that the nth levels start from n is equal to 1, n is equal up to n is equal to 4. So the diameter of these spherical shapes of n is equal to 4 is greater than the diameter of this S orbital. That's the meaning of this sentence, that the radius of the sphere of S orbital increases with proportional with the increase in what? With the increase in what? In the value of principal quantum number n. Right? So when you say that the radius, we may say that is the radius, possibly that is the center. You have to draw a good sphere, possibly mine is not good. But the issue is just the concept. So this S orbital is found in any principal quantum number. It's found in any principal quantum number. S orbital is found in any principal quantum number. So from n is equal to 1 to n is equal to infinity, say. The meanings of this sentence. Then we go to the shape of P orbital. Tell your neighbor the shape of P. Now we have to be ready to learn the shape of P orbital. Tell your neighbor, please. Be ready to learn the shape of the P orbital. So we say that the shape of P orbital is dumbbell. I'll draw it for you so you know the bell. So it's dumbbell, that is shape. Also, its radius of the its sizes increases with increase in the principal quantum number. The size of the P orbital increases with increase in the value of principal quantum number. And this principal quantum number, this means n. So what do we mean? We mean that the size of P orbital, size of p orbital of principal quantum number n is equal to 2 is greater than the size of p orbital n is equal to 3 is the best, n is equal to 3 is greater than the size of the p orbital of what? N is equal to 2. That's the point. So this p orbital appear in 3 dimensions. It means that they appear in 3 axes. So we have to draw it according to its 3 dimension. So basically the shape of this of p orbital, if you know the axis, is this. It's not just spherical, but it's just like this. So this is the number. So we say that there are 3 types of p orbital according to the axis. According to the axis. So you have this, for example, it is y-axis. So I think that I should mention them, draw each step. These are Roman 1 px orbital. So px orbital, its shape will be like this. This is y-axis, this is x-axis. So its dumb shell will be along the x-axis. Along the x-axis. So you can shade if you like. That is px orbital. We'll understand what it means of px, py, pz in next lectures, so stay tuned. Roman 3, we have also py orbital. Py orbital. Py orbital, the shape will be along the y-axis. This is the x-axis. So then the shape of the orbital will be along the y-axis. So that the shape for p subscript of y, or p orbital. Chemistry is beautiful. Essential atomic structure. Because if you are lazy, then you give up soon. Roman 3. Again, we have another p orbital, which is pz. So pz orbital. So this is the orbital along the z-axis, right? Along the z-axis. So suppose that this is also here we have a z-axis, right? And then here we have also a z-axis. These 3 axes are perpendicular to each other. So when you say that, let me draw and then I'll show you how are they perpendicular, because I used to teach students also advanced mathematics and the topic known as vector. I used to teach diploma students also basics engineering or basic vector for engineers and scientists. And also I used to teach vector to all-level students for basic mathematics. Do you like vector? So I will show you the three-dimensional. What does it mean? So, because this is two-dimensional, the blackboard is two-dimensional, it has only two axes. Since there's no way out we can show the three-dimensional, but this is what we call the PZ axis or PZ orbital. So if you label, this is what you have to label. So when you say about three-dimensional, I want just to give you a portion of the braid of mathematics, however that I'm teaching chemistry, but by God's grace also I'm a teacher of mathematics, I'm a teacher of chemistry. However that I'm teaching you chemistry, but I want to give you a piece of the braid because we are discussing about that concept. I would like just to tell you that it's true, and it is scientific and even mathematically proved that these three axes, X, Y, and Z, is dimensional, they should be perpendicular. But remember that the blackboard is two-dimensional. So two-dimensional, you just see there, it means that, let's say, for example, is the height against the length, the width and the length of the blackboard. So, in case you want to show these three axes, which are perpendicular to both, this is Y axis that you are familiar, this is the X axis. So you agree that these always are perpendicular to each other, right? So the issue is where the Z axis now. So, so this is horizontal, for example, axis. This is vertical axis.